Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 10, Solving Quadratic Equations with Complex Solutions. This is our last lesson in Unit 9, all right, and it's kind of the culmination of it, which is where we're going to be solving quadratic equations, equations with an x squared or an n squared or what have you, that actually have solutions that have an I in them. All right, so let's jump right into it because we've got all the tools we need. Now, complex solutions. As we saw in the last unit, the roots or zeros of any quadratic equation can be found using the quadratic formula. Now, since this formula contains a square root, right, up there, it is now fair to investigate solutions to quadratic equations where the quantity under the square root, which is known as the discriminant, is negative. So that's that b squared minus 4ac. You know, the stuff that isn't under the square root, the negative b and the division by 2a, those are just, real numbers, whatever they are, all right? But when b squared minus 4ac goes negative, and we've got the square root of a negative number, then we can have i's come up. Now, up to this point, we would have concluded that if the discriminant was negative, the quadratic had no solutions. And if we were really good about it, we said no real solutions. But now, if it's got a negative under there, it can have complex solutions. So let's jump right into one like that. Exercise number 1. Using the quadratic formula or completing the square to find all solutions, use the quadratic formula or completing the square to find all solutions to the following equation. Express your answers in simplest a plus bi form. All right. Well, truly, whether you use the quadratic formula or completing the square, it's fairly easy to solve this. In fact, I would almost claim that using completing the square is faster. But I think we'll start by using the quadratic formula since we were just talking about that discriminant piece. So let's take a look and do this problem together. Okay, well, we've got the quadratic formula up above, but, if we just think about our numbers, a equals 1, b equals negative 4, and c equals positive 29, then our solutions are going to be given by negative b plus or minus the square root of negative 4 squared minus 4 times a times c, all divided by 2 times a. Now, as usual, the most important thing here is making sure that you get that discriminant value correct. So if you need to, right, you take your calculator out and you use it to figure out what that value is. For me, I've already figured out that value and it happens to be negative 100. Okay? Again, prior to this, what we would have done is we would have said, well, I'm sorry, but that means that this has no solutions. Now, I know that the square root of negative 100 is simply 10i, or 10 times I. So I can now write this as 4 plus or minus 10 times I, all divided by 2. And I can distribute that 2, so I'll have 4 divided by 2 plus or minus 10 divided by 2i, and that's going to be 2 plus or minus 5 times I. So we've got two complex solutions, 2 plus 5i and 2 minus 5i. And we would get exactly the same thing if we did this by completing the square. All right, so that's it. And that really kind of gets at the heart of solving a quadratic equation that's got complex solutions, right? Prior to our work with imaginary numbers, at this point you would have had to stop and say, this equation's got no solutions. Now you can say it's got two complex solutions, 2 plus 5i and 2 minus 5i. All right, let's get some practice with this. It's pretty easy. All right, if our solutions can include complex numbers, then every quadratic equation can be solved for two solutions. Now, the two solutions may be the same number, all right? But that only happens if the discriminant is equal to 0. Most of the time, the two solutions are distinctly different. Here we go. Exercise number 2. Solve each of the following quadratic equations. Express your answers in simplest a plus bi form. So, spoiler alert, all of these things have complex solutions. In letter A, we have x squared minus 5x plus 30 is equal to 7x minus 10. Now recall, right, especially if we're going to use the quadratic formula, we need to have this thing equal to 0 before we do anything else. So pause the video now and see if you can solve letter A using the quadratic formula or completing the square, your choice, all right, and see if you can simplify the answers, which will definitely involve an imaginary component. Pause the video now and go ahead and work through that. All right, so let me first get everything equal to 0 by subtracting a 7x and adding a 10 to both sides. All right, that's going to leave me with x squared minus 12x plus 40 is equal to 0. If I'm going to use the quadratic formula, I've got a equals 1, b equals negative 12, and c equals 40. So I can now say x is equal to negative 12 plus or minus the square root of negative 12 squared minus 4 times 1 times 40, all divided by 2 times 1. That's going to leave me with x equals positive 12 plus or minus the square root of negative 16. That's a nice number underneath there, divided by 2. It's nice, not because of the negative, but because of the 16. So 16, negative 16, its square root is going to be 4i, so we get 12 plus or minus 4i divided by 2. And then when we distribute that division by 2, we'll get 6 plus or minus 2i. Let me make that look like a plus minus. There we go. All right, great. So 6 plus or minus 2i, as simple as that. Hopefully you got that. Let's take a look at letter B. Kind of more of the same. X squared plus 16x plus 15 is equal to 10x plus 4. Why don't you go ahead and try to solve that? Little spoiler, I think I'll do this one by completing the square, just so you see one of those again, but you can do it using completing the square or using the quadratic formula. It's up to you. Pause the video now and go ahead and work through that one. Oh well, okay. Regardless of whether I do the quadratic formula or completing the square, I do like to sort of get everything equal to 0. So what I'm going to do is I'm going to subtract a 10x and subtract a 4 from both sides. All right, that's going to leave me x squared plus 6x plus 11 is equal to 0. All right, now one of the bigger differences is if I'm going to go with completing the square, then I tend to move that constant over to the other side. So I'm going to end up having a negative 11 on the other side, which makes you wonder why I even put the 4 on the left-hand side in the first place. To complete the square, I'm going to take half of my b, which is 3. I'm going to square it and get 9. On this side, I'll add a 9 as well. What I do to the left, I must do to the right in terms of addition. This all then factors into, whoops, let's try that again, into x plus 3 quantity squared is equal to negative 2. I can now take the square root of both sides. I'll get x plus 3 is equal to plus or minus the square root of negative 2. Now, that's going to be plus or minus I times square root of 2, right? And that's because I can rewrite this as plus or minus the square root of negative 1 times the square root of 2. The square root of negative 1 becomes that I, the square root of 2 stays the way it is. And now I can subtract a 3 from both sides and I'll get x equals negative 3 plus or minus I times the square root of 2. One of the things I really like about completing the square, especially in a situation that lends itself naturally, and that's when the leading coefficient is equal to 1 and the linear coefficient is even. One of the things I like about it is that you don't have to like play around at the end with this division by 2, right? And that can actually really throw people off. It really can like mess with people. So for me, if I see a situation where my leading coefficient is 1 and my linear coefficient, the coefficient multiplying x, is even, which means taking half of it is easy, then I love completing the square, right? It's actually quite fast to get all the way down to here. Maybe even faster than the quadratic formula. But that's about it. There isn't much more in terms of solving a quadratic that has complex solutions. So let's talk a little bit more about what we can get from this procedure. Let's talk about the zeros of a parabola. There's an interesting connection between the x-intercepts, the zeros, of a parabola and complex roots with non-zero imaginary parts. I always have to throw that in because all numbers are complex, but if they've got non-zero imaginary parts, it means that there's an I sitting there. The next exercise will illustrate this important concept. Now let's take a look at number 3. Consider the parabola whose equation is y equals x squared minus 6x plus 13. Algebraically find the zeros of this parabola. Express your answers in simplest a plus bi form. All right, well, anytime we're looking for the zeros of a function, anytime we're looking for the zeros of the function, we always start by taking the function's equation, x squared minus 6x plus 13, and setting it equal to 0. Okay, so what I'd like you to do is now solve this and maybe use the quadratic formula to solve it. You could again use completing the square, leading coefficient of 1, right? Even coefficient there, so that's pretty easy. I guess either way, find the zeros of that parabola. All right, well, let's do it. I'm going to use the quadratic formula, I think, this time. I'm going to say a is 1, b is negative 6, c is 13. So x equals negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 13, all divided by 2 times 1. X is going to be positive 6 plus or minus the square root of negative 16 divided by 2. That's 6 plus or minus 4i divided by 2. And that's 3 plus or minus 2i. All right, so the zeros of this parabola are complex numbers that have a non-zero imaginary component. All right, great. Now, remember, the zeros typically are just another name for the x-intercept, right? Because they are the x values, right? They are the x values where the y value is equal to 0, right? And those are the x-intercepts. So now, what I'd like you to do in letter B, using your calculator, sketch a graph of the parabola on the axes below. Use the window indicated. All right, so just grab your calculator, throw this in as your function, use this as your window, negative 5 to 10 along the x-axis, negative 5 to 20 along the y-axis. Just get a sketch of that parabola. All right, well, I'm not going to bring the calculator out. That we've done a million times in this course at this point. There's our parabola. There's our parabola. And notice something, right? Since all parabolas have this general shape, all quadratic functions have this general shape, right? Its minimum point is right there. It never goes lower than that. So, letter C. From your answers to A and B, what can be said about parabolas whose zeros are complex roots with non-zero imaginary parts? In other words, what can you say about a function, right, that ends up having a quadratic function, that ends up having zeros that algebraically have an imaginary component to them? Take a look at that and look at that. What can you say about those x-intercepts? Pause the video now and give an explanation. All right, well, what we can say is that the parabola will never touch the x-axis. Or, better yet, i.e., it will not have any x-intercepts. Now it's kind of cool to understand why that is, right? So the x-axis is a real number line, meaning that the only types of numbers that show up on the x-axis are real numbers. But as soon as we've got a 0 that has an imaginary component to it, well then that could never show up on a number line that is completely and utterly real numbers. And so if we ever solve a quadratic and we find that it's got imaginary, non-zero imaginary components to its zeros, then that means that parabola will always miss the x-axis. Now it could miss the x-axis kind of looking like that, or it could miss the x-axis by kind of looking like this, but it will most certainly not intersect the x-axis, because if it did, well then wherever it intersected the x-axis should be the answers or the solutions to setting the equation equal to 0. All right, so how can we kind of summarize that? Well, we can summarize it by the discriminant. Let's take a look at this. The discriminant. The discriminant of a quadratic function f of x equals ax squared plus bx plus c is the quantity b squared minus 4ac. If the value of the discriminant is negative, then the function will have no real x-intercepts, i.e. it will not intersect the x-axis. All right? So again, this quantity is the quantity that's underneath the square root. And if that quantity is negative, then that will indicate that the parabola will not touch the x-axis. It's super duper cool. It's really kind of a neat connection between the graphical nature of a parabola and the algebraic nature of the quadratic formula. So let's take a look at exercise number 4. Use the discriminant of each of the following quadratics to determine whether it has x-intercepts. All right, now you could totally just go through the entire process. X equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. You could do all of that, right, to try to figure out whether or not these things have x-intercepts. But it's much easier to just use b squared minus 4ac. So let's do that in letter A, okay? So letter A, right, I'm going to just take a look at the quantity b squared minus 4ac. So that's going to be negative 3 squared minus 4 times 1 times negative 10. That's 9 plus 49, it's 9 plus 40, and that's 49. Now, again, think about this. If you were doing this procedure and you were going through the quadratic formula, this would be the number under the square root. This. Notice the discriminant doesn't actually include the square root. It's just the b squared minus 4ac. Because this is greater than 0, that means it has x-intercepts. All right? Doesn't matter that it's a perfect square. That's totally irrelevant. All right? The fact that it's greater than 0 tells us that we do have x-intercepts, and that's all we're looking for here. Let's do letter B together as well, and then I'll have you do letter C on your own. Letter B. Here we have the parabola y equals x squared plus 6x plus 10. So if I'm looking for b squared minus 4ac in this case, that's going to be 6 squared minus 4 times 1 times 10. That's 36 minus 40, and that's equal to negative 4. Now, that is less than 0. And since that's less than 0, it does not have x-intercepts. If you were doing the quadratic formula and you cranked through all of it, right, then what we would be forced to do is take the square root of a negative number, which would leave us with an I in our answer, and it would mean that this parabola doesn't intersect the x-axis. Why don't you go ahead and do letter C on your own and see if this parabola, when graphed, would intersect the x-axis. All right, one more time. Let's do b squared minus 4ac. Maybe do a few lines there. That's going to be 3 squared minus 4 times 2 times 5. That's going to be 9 minus 40. That's negative 31. And again, I don't care about anything except for the fact that it's less than 0, which means that again, it does not have, let's try that again, it does not have x-intercepts. All right, and that's it. Right? So the discriminant is a very powerful way of understanding whether or not a parabola, a quadratic function, will intersect the x-axis or not. Let's take a look at one final problem. Exercise number 5. Which of the following quadratic functions, when graphed, would not cross the x-axis? Verify by graphing on your calculator. All right, well, the key here will be to calculate the discriminant for each one of them and find the one where the discriminant is negative. So what I'd like you to do now is play around with all of these and see which one has a negative discriminant value. All right, well obviously I've worked it out and I don't want to work out the discriminant on every one of them, but just for a moment, let's work out the discriminant on number 1, just for a second. So on this one, b squared minus 4ac would be equal to 5 squared minus 4 times 2 times negative 3. That would be 25 plus 24, right? Yep, which would be equal to 49. That's greater than 0, so that would cross the x-axis, right? That would have x-intercepts. Now the one that's actually our correct choice, because again, we could go through every one of those, is choice 3. And let's take a look at why. Right here, b squared minus 4ac ends up being negative 4 squared minus 4 times 5, which would be 16 minus 80, which would be negative 64. And that's less than 0, right? So because that discriminant is less than 0, that one should not have any x-intercepts. And let's take a look. Let's verify that on our calculator. So let me just exit this real quick. Let me bring up my calculator. I'm going to add a page and a graph. Let's take a look. In theory, if I'm right, 4x squared minus 4x plus 5 should not hit the x-axis. Now that may not be the greatest window for it, but you can kind of see that it's not going to happen. Now let me just take a look really quick. Let me go into my window a bit and my window settings. I'm going to make my Y window just a bit bigger, maybe go up to 20. And there it's a little bit more obvious, right? We've got a parabola, comes down here, opens back upward. Our minimum value is above the x-axis and it's pointing upward on both ends. That thing never hits the x-axis. On the other hand, right, just for a moment, let's take a look at that one in number 1, right? If I go back into menu and I put my first function in there, 2x squared, where we had a actual positive discriminant, plus 5x minus 3. In this case, we see that we most certainly do have x-intercepts. And again, that's because in number 1, we have a discriminant that's positive, and in choice 3, we have a discriminant that is negative. Choice 2 and choice 4 would also have discriminants that are positive, and therefore would also intersect the x-axis. All right, so let's go and wrap this thing up. All right, so today we were finally able to solve a quadratic equation using the quadratic formula or completing the square that ended up having negatives under the square root. The key is that the two solutions that we got both had non-zero imaginary components. In other words, they looked like 3 plus or minus 2i, or negative 7 plus or minus I times the square root of 2. Things like that, right? Before this lesson, before we ever knew about imaginary numbers, which we've studied for all of 3 lessons now, that's it, right? Before that, we would have gotten to that step and said, this equation has no solutions, right? None whatsoever. Now we can say it does have solutions, but those solutions are complex numbers that have an I component to them. We also looked at how we can relate the discriminant, the b squared minus 4ac underneath the square root symbol of the quadratic formula, to whether or not the graph of a parabola touches the x-axis. If that number is negative, if b squared minus 4ac is negative, then we have a parabola that completely misses the x-axis. On the other hand, if that value is positive, then our parabola will cross the x-axis. All right. Well, you'll work a lot more with complex numbers in pre-calculus. We probably won't see them much more in this course, maybe a little bit here, a little bit there, but they're not a big part of Algebra 2 moving forward. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.